So for the next couple questions, I'm going to occasionally pause the video, write out the dimensional analysis that's going on, and then pause it. You don't need to watch me slowly handwrite and correct all the mistakes I make. So if you just see some numbers appear, it's because I stopped or paused the video to do the math in the background. 23 through 26 this time. Switch to red, that'll be fun. Copper is heated in an excess sulfur to make copper 1 sulfide. That's what's being formed. Wait a minute, there's no equation being given. I'm going to have to figure out what the equation is before I even work with any of that stoich stuff. So you read the question and then you have to parse apart the equation. Let me do that for a second. So there we go. It was copper's reacting with sulfur to produce copper 1 sulfide. I had to use the charge of the copper to figure out the formula of copper sulfide, but I can't just end up with 2 coppers unless I start with them. So I had to balance that equation first. In the experiment, 1.5 grams of copper is heated to yield that much copper sulfide. That's what's actually produced. That's what it yielded when they did it. So this value here is what we call an actual yield. 1.76 grams of the copper sulfide is the actual yield. And we're given 1.50 grams of copper, and we have an excess of this, so we don't care about, we're not going to run out of sulfur, really, is what we're saying there. So now we have to set up the stoichiometry, to figure out the theoretical yield. Theoretical meaning, based upon the theories of stoichiometry, the mole ratios and everything, what should happen. And we'll compare this theoretical yield to the actual to get that percent yield. That's actual over theoretical times 100 to get the percent yield. Let me go ahead and set up the dimensional analysis there. All right, here we are with the numbers all written into place. I started with the given that they were actually reacting. I was working through the theoretical yield, so this is copper. So I say, well, if I've got copper, let me put the molar mass to convert it to moles. And then for every 2 moles of copper, I can only make 1 mole of copper sulfide. 1 mole of copper sulfide couldn't fit my molar mass into that space and make it legible for you to read. It's hard enough on a good day, much less when I squish it in to read my handwriting. So it's 159.16 grams of copper sulfide. I set all that dimensional analysis up to convert the units over and got a theoretical yield of 1.87 grams of copper sulfide. So that's the first answer. What's the theoretical yield? 1.87 grams. What's the percent yield? Got to compare what they were able to get, 1.76, to what they should have gotten, 1.87. It's just a division, actual divided by theoretical, 94.1% yield. Yes, I was worried about sig figs when I did this. I said I have 3 sig figs. I have 3 sig figs. Didn't lose any in the dimensional analysis. I still have 3 sig figs. So I did 1.76, which is 3, divided by 3, times 100, which is infinity. 94.1 is 3 sig figs. So careful with your sig figs the whole time. Why don't my numbers match up perfectly? My numbers, I used a different periodic table when I did this, actually. So this value here, nope, I'm wrong. So this should have been 1.88. And looking back in my calculator right now, and I didn't round properly. So 1.88, so 1.76 divided by 1.88 is 93.6%. Yeah, I would have lost the point for that. You have to get the right value. I would have lost the sig fig point, actually, because I did my rounding wrong along the way, which is really annoying to do all that work correctly on a problem and then lose a point for significant figures. Anyway, let's go on to the next question, 24. Similar idea, silver and sulfur is heated to make silver sulfide. This time at least they gave us the equation because it's a kind of a weird one. Sulfur makes these octagon rings with itself, which is kind of different compared to a lot of other elements. But anyway, what mass of silver sulfide is produced from a mixture of 2 grams and 2 grams? So this one's different. You're going to have a limiting and excess reactant. Let me go ahead and set this stuff up. So dimensional analysis is all set up everything's canceled out properly. 2 grams, 107.87 to 1 mole of silver. For every 16 silvers, there's 8 moles of silver sulfide. 1 mole of silver sulfide, 247.8. What's nice is this 247.8 gets used in both problems. It's limiting excess, so you're going to go to the same endpoint for both of them. And we only use one answer, and that's going to be the smaller of the two answers. So at 2.3 grams, you will run out of silver. At 2.3 grams, you're going to run out of silver. Now, since there's not percent yield or anything going on like that with this question, we're assuming that all 2.3 grams are produced. Now, there's two ways to answer part B. One is, again, using dimensional analysis. You now know that the silver is limiting and the sulfur is not. So you could say, 2 grams of silver, and you could go 2 grams of sulfur that would be needed. And you could figure out how much was used and subtract that, and you would get that 0.3 grams of sulfur were used. You could subtract it from the 2.0 you have, and the leftover would be 1.7. That's actually the harder way using dimensional analysis. For part B, the easiest way is the law of conservation of mass. So check this out. You're starting off with 2 grams of sulfur and 2 grams of silver, right? Sulfur and 2 grams of silver. But you're only making 2.3 grams of product. That doesn't add up. 2 plus 2 should be 4, not 2.3. So there's some leftover sulfur. So you just use some simple subtraction. All of this is being used up to get into the silver. So you could subtract that. You know that there's 0.3 grams of that is from the sulfur then. 2 grams of this 2.3 grams is from the silver. The 0.3 grams is from the sulfur. So they only used 0.3, so that's 1.7 grams of sulfur that are still sitting over here. That's one approach to do it. Another approach is just do simple math. If this is 2 plus 2 is equal to 2.3 plus everything that's left, and everything that's left is the unused sulfur, the 1.7 grams of sulfur. So there's a couple of logical approaches. Each of those approaches better yield the same answer, though, or there's a logical mistake there. I like the law of conservation of mass, that the total on one side, starting off with 4 grams, you still have to have 4 grams total at the end. And this is 4 grams, 2.3 grams of silver sulfide, and the rest of the sulfur that didn't react is 1.7 grams of sulfur. All right. 25, I'm not going to bother to do 25. Calculate the molar mass, go to the periodic table, add the pieces together. The only thing I'm going to say is with D, this is not usually how D would be written. It would probably be written CuCl2 dot 6 waters. So this would be called copper Roman numeral 2 chloride hexahydride. Hexahydride means there's 6 waters attached to that compound. And you just calculate the molar mass of copper chloride, 6 waters, and add them together as if it was all one compound. And C is also kind of goofy. Do C2H4, 4 fluorines, add that together, and then multiply it by 500, which gives you a pretty insane answer. But let's go to 26, which is probably the only reason you're watching this video anyway, because 26 really throws some people for a loop. We have this unknown element, X. It can have 2 possible oxidation states. So you have X dichloride and X tetrachloride. Treatment of 10 grams of X with excess chlorine yields 2.55 grams. Let's look at that. So we have XCl2 plus chlorine produces XCl4. Okay, let's write down what else we have. We have 12.55 grams of XCl4. and we had 10 grams of this compound, well, what's missing? The amount of chlorine that attached onto it. And this should be easy to figure out. If it's going from 10 to 12.55, then 2.55 grams of chlorine are in that, were added onto it. Not only that, but if we know the mass of Cl2, then we also know the mass of this Cl2. So we could say in this compound here, we would know the mass of X and the 4 chlorines. And that could be really useful for figuring out molar masses in a little bit. Let's first, X would be 7.45 grams would be the amount of element X in that compound. I just did 10 minus, that's 10 minus the 2.55 to get the chlorine out of that compound to figure out how much X weighs. So it doesn't feel like I've gotten much closer to the molar mass, but I actually have, because molar ratios are always the same. For instance, if you have carbon dioxide, that's always a 12 grams of carbon for every 44 total grams of carbon dioxide. So if I gave you 88 grams of carbon dioxide, well, that would mean there were 24 grams of carbon. That is a constant ratio. It's called the law of constant composition. It's really useful in a problem like this. So, what can we do? We can go to the periodic table and use this data and figure out the missing molar mass. So let's see, what do we know? We know that the mass of a compound is 7.45 grams of X for every, how many grams of chlorine are in the XCl4? Or just the XCl2. Oh, in the XCl2, there's 2.55 grams of Cl2. So that's the grams of chlorine that are in XCl2. That's the grams of X in XCl2. So what I'm going to do is say that should be directly related to what we find in the periodic table. So I'm going to go to the periodic table and find the molar mass for Cl2. Chlorine is 35.45 times 2. Let me pause this. All right, so a chlorine on the periodic table is 35.45. There's 2 chlorines. So this is the molar mass for Cl2. That's directly off the periodic table. This is from the data. But this 7.45 ratio of element X to that mass of chlorine has to be equal to the molar mass of X, which we don't know, divided by the molar mass of Cl2. So I set this up as a ratio. Molar mass divided by molar mass is equal to actual mass divided by actual mass. So if I solve for this value here, I'll know the molar mass of the compound. So do some cross multiplying, and we find out that it's 207.1 grams of X. That's the molar mass of X. So you go to a periodic table and you see anything in the 207 range. And lead, 207.2, is darn close to 207.1. And if you think about sig figs, we have 4 sig figs here. Really, I should only have 3. After I did subtraction here, I lost a sig fig. But anyway, and my division here, I have 3 sig figs versus 3 sig figs. So I only really have the first 3 sig figs. 207 is the mass of lead. Plus, lead is one of those elements that can have multiple charges. You can often have lead as a +2 or lead as a +4. So that makes sense in terms of those 2 formulas. So again, and I repeat this, the law of constant composition is uber useful, super useful. I took the actual mass of X from the data, the actual mass of chlorine based on the data. This is the molar mass of chlorine based on the periodic table, and the missing mass here would be the molar mass. If I solve for that molar mass, which I did, I can identify the element, which is a really nice way of finding an unknown element and a key skill in AP Chemistry. I would review this one twice.